Hi guys, welcome to the fourth lesson in the renal series. For this lesson, we're going to talk about how the kidney handles sodium, chloride, and water. These are three extremely important substances in terms of renal handling. In fact, it's really the core of renal physiology. Understanding how these molecules are handled by the kidney and what controls them, which will be a large part of the topic of the next lesson, will be a big deal for you guys. Let's start off by talking a little bit about what the kidney's role in all this is, and remember that essentially your kidneys are maintaining homeostasis, okay? And their job over a long period of time, short term things may go up, they may go down, but over a long period of time, their job is to balance the intake of salt and water with the outflow, which is mostly through the kidney, about 90%, okay? So ultimately, if you eat so many milligrams of sodium chloride, your kidney will get rid of most of that over the course of a day, so that what goes in comes out, all right? Now, short term, things may go up, things may go down, it may depend on your hydration status, et cetera, et cetera, et cetera. But overall, over a long period of time, the input has to equal the output, all right? So all three of these molecules are freely filtered, and usually the vast majority of what's filtered is reabsorbed, and huge amounts of energy are used to make sure that they get reabsorbed and retained within the system. So when we talk about regulation of the levels of the excretion of these things, bear in mind we're talking about a fairly small fraction of the total that the kidney actually sees. These molecules are all normally absorbed and not secreted, okay? So some generalizations before we get started. Sodium resorption is active, and it is powered by the basolateral sodium-potassium ATPase. So the vast majority of epithelia have this transporter, and as I pointed out in an earlier lesson, they use that sodium-potassium ATPase and the gradients that it generates, particularly for sodium, to drive the transport of substances across the epithelial layer. Chloride reabsorption is passive. It is both paracellular and transcellular, but basically what chloride does is it follows sodium, because as you guys know, you have to maintain electron neutrality in your body, with the exception of very, very small fractions of ions that go into generating voltage across a membrane. If you transport a cation, an anion has to go with it. And the majority of the time, the anions involved here are chloride, or as you will find out in a moment, bicarb. So chloride pretty much follows sodium around, and that's the way it's handled. Water reabsorption is by osmosis, okay? That is usually secondary to reabsorption of solute. Primarily sodium is what drives it. So a solute will be transported across the epithelial bilayer. That will locally increase the osmolarity in the interstitial space if you're reabsorbing, and the water will follow that osmotic gradient, okay? Usually wherever you see sodium transport, if water is allowed to cross the membrane, and we'll get to that in a moment, water will follow, okay? All right. It'll either follow sodium or the solutes that are sodium dependent. All right, so a quick overview of sodium reabsorption along the nephron. First of all, like I said, all three molecules freely filtered. So at this point, the the concentration of sodium in the Bowman's capsule is equal to the sodium in the plasma, all right? 65% of what's filtered is reabsorbed in the proximal tubule. So you get rid of the vast majority of the sodium right away. In the proximal tubule, we'll talk about the details of that. 25% is reabsorbed in the ascending loop of Henle. There is a specialized sodium transporter, the sodium-potassium 2-chloride co-transporter that takes care of that. And 5% is reabsorbed in the distal convoluted tubule. And 5% is reabsorbed in the collecting duct here. And then about 1% ends up in the urine, okay? So that's a quick round the horn there. Sodium is pretty much reabsorbed in every segment. So in the proximal tubule, the way this works, the filtered sodium in the tubular lumen gets across the apical membrane in a variety of different ways, it's often sodium hooked to transport, like transport of glucose, which we talked about earlier. But the sodium gets across one way or another, okay? And it's just sort of a variety of different ways. Do bear in mind, like I said, glucose, other solutes are linked to sodium reabsorption here through the transport a lot of the time. The sodium-potassium ATPase in the basolateral membrane drives all this. It transports sodium into the interstitial space. That does two things. It keeps the sodium low in the cell, which creates a gradient from the tubular lumen into the interior of the cell, which allows sodium to go down that gradient, okay? So it drives the sodium transport into the cell across the apical membrane, and then that sodium, number 2, is transported here, and then is eventually transported out of the cell across the basolateral membrane into the interstitial space by that ATPase. So it plays a dual role here. It's transporting the sodium out across, and also maintaining the gradient for apical membrane. Okay. Without the sodium ATPase, the sodium gradient goes away, and this transport does not happen. So this is all powered by that pump. It's extremely important. All right, chloride reabsorption, parallel sodium reabsorption. Because of electroneutrality, you have, if you transport a cation, a sodium ion, then some sort of an ion has to go with it to keep your solution electrically neutral. And the major anions that have to go with the sodium are chloride and potassium, which I'll show you in a moment. So the chloride reabsorption more or less parallels the sodium. So if 65% of the filtered sodium goes out the proximal tubule, 65% of the chloride goes out, all right? And the same with the other segments. All right, so there are two routes of chloride reabsorption. The easy one, it gets through the tight junctions in the, so the tight junctions, maybe not so tight, and they're permeate to chloride, and so the chloride can get through. So if you're talking about a sodium transport, the chloride can get through between the cells paracellularly through the tight junctions and just follow the electrochemical gradient. Transcellular transport of chloride is kind of complicated, but all you need to know for now is that the net result is 1 sodium in for 1 chloride in, so it is effectively, indirectly, a sodium chloride co-transport or symport, okay? And then on the basolateral membrane, of course, you have your sodium-potassium pump driving this uptake, and a potassium chloride co-transporter will take the chloride across the basolateral membrane. All right? Good. Okay, so why don't we stop here, and we'll pick up in the next video with water handling.